Welcome back, students, after the mid-semester examination. I hope you did all right. Before the mid-sems, we reached all the way till emitter follower amplifier. So in this lecture, I'm going to finish up emitter follower amplifier using, of course, bipolar junction transistors. We will add some nuances to it, and we will study some of the specific details about emitter follower amplifier, where it is used, why is it so important. After which we will start with source follower using MOSFET transistor, and then this lecture would be the concluding lecture for all different single transistor amplifiers configuration. Thank you. In the previous lecture, we talked about common collector amplifier or emitter follower, and we did a very simple circuit representation of the emitter follower. In this lecture, first we will start off with adding more details to the amplifier. So we already know that for this amplifier, V out over V in is equal to 1, and R out looking back in is equal to 1 divided by GM1 of the transistor. So this is a very simplistic representation of emitter follower or common collector amplifier. Now we will add more nuances to this circuit and understand the impact. The first thing we are going to do is add a base resistor here, RB. And now we will look at what happens to R out in presence of RB. What I would like you to do is again draw the small signal circuit and then figure out R out. How do you figure out R out? We apply a V test and we look at the I test, and ratio of V test over I test will give us R out. And when we are doing this analysis, of course, we have to zero out any other independent source. For example, in this case would be V in. So I would like you to do KCL at this node and figure out what's the value of R out, which is V test divided by I test. So let me walk you through the expressions here quickly. I'm sure you already figured it out. The current I test here is given by current flowing in this side and this side, which is given by this expression. I'm substituting for V pi, which is the potential drop over there, as a resistive divider expression from V test to ground, which is given by R pi divided by R pi plus RB times Vt. That would be the resistive divider expression. And you have to take care of the signs properly. So final expression you're going to get out of this is output resistance R out is given by 1 over Gm, which used to be the case when we did not have a base resistance Rb. Along with that, the new term which we are seeing is Rb divided by beta. So what this analysis is telling us is when we are looking into the emitter of a common collector amplifier or emitter follower amplifier, whatever is resistance is at the base gets divided by the current gain of the amplifier. So this is one key thing to remember from this analysis. Next thing we are going to do is we are going to add more layers here. One is, in this particular case, we ignored the output resistance of transistor Q1, and also we did not have any load resistance here, actual load resistance. So in the next circuit, we are going to add those two and see its effect on the gain R in and R out of the amplifier. Let's redraw the circuit. You can draw the small signal circuit and then solve for three things. I'm just going to show you the final results, but I would expect you to do them on your own. So what are we looking for? We are looking for three things. One is V out over V in. Second expression I'm looking for is R in, and third expression is R out. So R in we are looking here, and R out we are looking in this way. So you can pause the video, do it by yourself, and then compare it with the analysis I'm showing you. Okay, so let's pause and review the equations one more time. So this expression is essentially KCL at this particular node, and this is a voltage divider expression where we are looking at what is the voltage across this resistor in RB plus RPi, and once you substitute, you will get your gain, which is this term, which is RL prime divided by RL prime plus RB divided by beta plus 1 over GM. RL prime, the way to look at it is, if you look at these two resistors, R out and RL, they are connected across V out to ground in parallel. So for sake of convenience, we call them RL prime. Okay, and input resistance, you can also figure out the input resistance is given by this expression, which is R pi, and then you get a GM, R pi, and you get a beta multiplier effect of any resistance which is connected at the emitter. So in this particular case, we have RL prime, which is RL in parallel with R out. So that in effect gets multiplied by beta, the current gain of the transistor. That's what your Rn will look like. And R out is going to be resistance looking back, and that will have, already we did in the previous analysis, which is going to look like reciprocal of GM plus resistance at the base, which gets divided by the beta, and that whole expression in parallel with RL prime, which is again RL and R out in parallel. Okay, this may be too much to digest, but you need to really go through the analysis by yourself and convince yourself. What we will be capturing eventually is all these rule of thumbs. For example, one rule of thumb is any resistance at the base that resistance will get divided by the beta of the transistor when we are looking at it from the emitter point of view. And any resistance at the emitter looking outward will get, what will happen to that resistance, that will get multiplied by beta, which is what we saw over here. So that's the rule of thumb that we come back with. Let's go through one example so that all these things become very clear. So the emitter follower amplifier or common collector amplifier, you may wonder that you never get gain from this amplifier. You only get gain, maximum gain you can get is 1, then why do we really use it? So this particular example will demonstrate the utility of emitter follower or common collector amplifier. So let's start off with a standard common emitter amplifier, which you have seen. For example, let's look at this amplifier. So if we just look at this amplifier, we know the gain of this amplifier is going to be, what is the gain of this amplifier? By now you should know it it should be on your fingertips. GM times RL minus GM times RL, and in this case this should be, GM is, since I given you 1 milliamp, that would be 1 milliamp divided by 26 millivolts multiplied by 2K. And this number will, I think, come out to be something like 80. So this amplifier gives you gain of 80. Now if we decide to use this amplifier to drive, let's say, a speaker, for example, the circuit will get modified like this. We would add a blocking capacitor, and then we will connect a speaker. The speaker resistance is typically something like an 8 ohms. As soon as you add 8 ohms, what will be our gain? This 8 ohms will come in parallel with 2K and will dominate, as a result of which our new gain is going to look like minus GM times 8 ohms, and that's going to look like minus 1 milliamp divided by 26 millivolts multiplied by 8, and this number is going to come out to be something like 0.3. So quickly you can see that this 8 ohms speaker resistance will load our amplifier, and our gain will drop from minus 80 to maybe minus 0.3, something like that. So this is bad news. So our amplifier ceases to act like an amplifier. So how do we solve this problem? Enter emitter follower. So what we will do is we will insert emitter follower in this case. So follow my train of thought. And I'm going to add emitter follower here, which is okay. Now let's see what happens. First of all, Let's start looking at resistances from different nodes. Let's denote that this node is called A and this is our V out. So from the previous analysis, first thing is if we look at resistance at node A here, R in, that is given by whatever is the resistance connected at the emitter, and that would get multiplied by beta of the transistor. So we can say that R in is given by R in, which is here, that is given by R pi 2 plus beta times RL. And in this case, beta is 100 and RL is your 8 ohms. What is R pi 2? R pi 2 is beta divided by GM2. Okay. Let's also calculate GM2 for the transistor Q2. So GM2 is equal to 10 milliamps divided by 26 millivolts, which is equal to 0.38, and the unit is MHO, which is reverse of ohms, okay, also called Siemens unit. So we can substitute in Rn beta divided by GM2 plus beta times RL. So this is going to be equal to 100 1 divided by 0.38 plus RL is 8 ohms. So this number is going to come out to be 1060 ohms. So resistance looking into the base of Q2 is now looking like 1060 ohms. This is 1060 ohms. So what is the gain of the first stage, which is going from V in to node A? So gain from V in to node A is going to be equal to GM1 times RL. RL is going to be 2K in parallel with 1.06K negative. So this is going to look like 1 milliamp divided by 26 millivolts multiplied by 693 ohms, and that will be approximately equal to minus 27. Also gain from node A to V out. What is that going to be? That we just did it couple of maybe in the previous lecture at the tail end, and that is going to look like 1 divided by R pi 2 plus GM2 divided by 1 divided by RL plus 1 divided by R pi 2 plus GM2. Now R pi 2 reciprocal of R pi 2 is equal to GM2 divided by beta. So we can ignore this piece and the gain will look like GM2 RL divided by 1 plus GM2 RL approximately. So this number is going to be 0.38 multiplied by 8 ohms and 1 plus 0.38 multiplied by 8 ohms. We don't get gain, but we actually get a loss. So we get 0.75. So what did we figure out so far? From input to node A, we got gain of 27 approximately, and from node A to output, we got a gain of 0.75. So total gain is going to be equal to, overall gain will be 27 times 0.75, which is equal to 20.3. We are able to drive 8 ohms low resistance load using emitter follower and still get gain, reasonable gain, factor of 20. This is the advantage of using emitter follower. Many times this circuit is also called a driver circuit. For example, you achieve all the gain that you desire using a series of amplifiers, cascade of amplifiers, and then at the last point where we need to drive a low resistance, that's when you use a stage like an emitter follower, or we call it a driver stage, to finally drive the low resistance. After emitter follower, we will start looking at its MOSFET counterpart, which is common drain amplifier, or also called source follower. So please draw the schematic. In this case, transistor M1 is assumed to be in saturation, so there is a proper bias voltage VB is applied at the gate of the transistor. So you can do small signal analysis, in which you will see so you can quickly see the VGS has to be 0, because at the output there is no place for current to flow, because I is a constant current source. When we go for AC analysis, we remove it, and in this particular circuit the GM VGS current source has nowhere to flow at the output node. Hence that has to be 0, which means VGS will be 0, so V out is equal to V input. So which tells us that the gain is, it's a unity gain amplifier, just like what we saw in emitter follower case. Let's figure out the value of R out in this case. So what we are interested in is R out. Looking back, so for R out we are going to do small signal analysis. Here again we will ground the input. This is grounded and this is GMVGS, and to calculate R out we are going to apply V test and we are going to measure I test. So here you can see that I test is nothing but minus GMVGS, which is nothing but minus GM minus VT, which is equal to GM VT IT. R out is equal to 1 over GM of the transistor. Very similar result like what we have seen before. So I'm going to show you another way to look at this circuit. So we can model the source follower as follows. The output resistance is 1 over GM. So we can look at it like a Thevenin equivalent looking back from the output. So Thevenin equivalent tells us that your source Vin open circuit is going to show up straight away at the V out. So Thevenin equivalent will look like Vin, and output resistance is going to look like 1 over GM. And this would be our equivalent representation of a source follower looking from the output back in. Now we can use this circuit to quickly write other expressions. So for example, we want to figure out effect of transistor R out and load resistance. How would we do that? So let's do that. Let's draw the circuit first and then I can explain it to you. So for transistor M1, we can draw R out as a dotted line over here, and also we can draw our load resistor at this node. So compared to our previous model, we can say that we can use our Thevenin equivalent looking back into this circuit, and that will tell us that we have this circuit Vin 1 over GM of the transistor. Along with it, the load is equivalently going to look like RL in parallel with R out, which is these two are going to show up over here. So now we can calculate the new gain, which is V out here. V out over Vin is going to look like resistive divider. V out is across this, and then we have 1 over GM in series, so it's going to look like RL parallel with R out divided by 1 over GM plus RL parallel R out. Another interesting aspect of this circuit is how do we implement this current source I. So in reality, the current source is designed like this. We would connect another transistor, another NMOS transistor M2, and then we would connect its gate to V bias or DC voltage. If you look at this circuit, you can say that the current IDS of M2, assuming transistor M2 is in saturation, is going to be constant, fairly independent of the drain voltage if we ignore the channel length modulation. And this whole analysis will hold true. If we want to account for channel length modulation, then this circuit will get modified as follows. this particular transistor will have its own RO2. Let's call this RO1. And now our gain expression will look like this. RO1 parallel with RO2. Here also RO1 parallel with RO2, and this will become GM1. So this is a quick way to do the analysis, and this is a way to implement a current source. To keep RO2 as high as possible, the transistor width and transistor length. So the question for you is, what would you do with W and L to keep RO2 high? Think about it, and if you don't remember, you need to go back and look at it, because this is an important concept. You should by now know it really well. Another question that you will encounter if you go for a interview is the following, and I like to teach you this because there is some subtlety involved that you need to appreciate. So somebody may ask you, hey, what is the resistance looking into the source of this transistor, Rin? And a quick answer people tend to give is 1 divided by GM of the transistor, GM1 of the transistor. So this answer is not exactly correct, and I would like to explain it to you. So follow my train of thought. First of all, what really matters is what's connected at the drain of the transistor. So in this case, I have shown you there is a resistance called Z we have connected at the drain, and we can draw a small signal analysis to appreciate this. So go ahead and draw the small signal analysis for this circuit. Now you can quickly see the Rin is given by Vt divided by It. What I would like you to imagine is what happens if Z is equal to infinite. For example, it's a current source with a very high output resistance. You can quickly see that if Z is infinite, then the value of the current It is going to be 0. And if It is equal to 0, then expression for Rin, which is equal to Vt divided by It, is going to be infinite. So right there, this quick answer of Rin equal to 1 over Gm of transistor M1 when we are looking at the source is invalid. So let's do a little more of a due diligence and figure out what the value of Rin is in presence of Z, resistance Z at the drain. So go ahead and write the current KCL KVL and come out with value of Rin. Please do it on your own. I hope you have gone through the equations here. Now here is the final point I would like to elaborate on, which is Rin is given by reciprocal of Gm plus Z divided by GM R out. So what this expression is telling you is, if Z is small, then yes, you're right, the resistance Rin is going to be 1 over Gm. However, if Z is large, then the resistance at the drain gets divided by the gain of the amplifier, intrinsic gain of the amplifier, which is GM R out. So this is the point I would like you to remember. I would like you to recall what we learned in the earlier lecture for the MOSFET, which is called body effect. So body effect, let me write it again. So this is a recap from our previous lecture. What this is telling you is the threshold voltage of the device changes depending upon the potential difference between body and the source. So just like the drain current changes because of potential difference between the gate and source, you could also say that the drain current changes due to potential difference between body or bulk and source, since VTH is changing. We can call body or the bulk also as a gate. However, it's called like a backgate. So body is also called backgate. So there are two terminals which can control the current of a saturated MOSFET transistor. One of them is the regular gate and the second one is the backgate. Now we will try to figure out if body potential has an effect on the drain current, then what is the transconductance? Okay, the backgate transconductance of the MOSFET in saturation. So what we are trying to figure out is GMB. B denotes bulk or backgate, and that is given by del ID by del VBS. And in this case, we would assume VGS and VDS are constant. So when we calculated our regular GM, we had VGS in this location. So for backgate transconductance, we are going to calculate del ID by del VBS. So how do we figure this out? We start from our basic saturated transistor equation, which is ID is equal to half mu n Cox W by L VGS minus VTH square. For now, I'm ignoring the channel length modulation because it doesn't add anything right now. And then we can calculate del ID by del VBS is equal to del ID chain rule by del VTH and del VTH by del VBS. The key thing here is VTH is function of source to bulk voltage, and we have to make sure that we take into account the polarities. So the first thing is del ID by del VTH. This is nothing but minus GM, okay, because there is a negative sign due to minus here. So this will look like minus GM, and if you calculate the expression for del VTH by del BS, that will come out to be minus gamma 2 times square root of 2 phi f plus VSB. The negative sign is because we have SB here and VBS here. So the final result is a factor like zeta times GM, our original transconductance. And this factor is somewhere between the range 0.1 to 0.3. So this is our GMB. Now when we create small signal model to include this effect, it's going to look like this. For example, our usual MOSFET small signal analysis looks like this. GM, VGS, and we have R out, and this is our gate, this is our drain, and this is our source, and here is our plus minus VGS. Now we have brought in one more terminal, which is the bulk or the body, okay, and here is our potential VBS, the backgate potential. So this will again insert another transconductance, which is GMB times VBS. So this is due to body effect, and generally most of the time you have the source and bulk connected together. However, many times if they are not connected together, then you need to include this effect. And I'm going to show you an example when they are not connected together. So when we look at a standard digital CMOS process, if you remember, I had asked you to do the cross section, then let's say you may have one transistor which looks like this, and then there is a bulk here, and you may have another NMOS transistor that looks like this, and it has its own bulk. So this is N plus, N plus, P plus, N plus, N plus, P plus, and this is our substrate, P minus substrate, and this becomes our bulk connection, and this is our bulk connection. So you can see that the two bulk connections over here between these two, they are shorted because P plus is going to P minus. So in a standard digital CMOS process, all the NMOSs are in the native substrate, the P minus substrate. So you cannot independently control their bulk. This bulk has to be connected to the most negative potential. So if we look at our original example of a source follower circuit, here we have this as a V out, this is V in, and this is VDD. When we did the first cut analysis, we ignored the body effect. So we assumed that this is actually connected to its own source, like this. However, as I explained just a few minutes ago, that is not possible in a standard digital CMOS process. So in that case, what happens is your bulk is actually connected to the most negative potential, which is ground in this case. As soon as you do that, you will have body effect for this transistor M1. So we can now do our analysis including the body effect. The small signal model is going to look like this. V in, and here is our bulk, which is connected to ground. So in this case, you can see that GM VGS is equal to minus GMB VBS. So we can say this is our V out. So let's write the expression GM V in minus V out is equal to GMB times V out. And here we go, we get V out divided by V in is equal to GM divided by GM plus GMB, which is equal to 1 divided by 1 plus the eta factor. So this should be less than 1. So in the MOSFET case, our gain is definitely less than 1 because of the body effect. Now you can also prove yourself what is R out, which is resistance looking back, and you will see that it will look like 1 over GM plus GMB. And you can also do yet another level of analysis to include the effect of RL and R out, and I have given that to you in the notes, but it's just a bunch of mechanics to go through and prove the same results. So every place you will see that the GM now gets replaced with GM plus GMB. So rule of thumb again here is whenever you see a circuit where you don't define your backgate connection, then you have to do your first cut analysis without the body effect, and if you know if it's an NMOS, then you have to look at the body effect and see its impact on your analysis. So body effect essentially complicates things slightly. So this kind of ends all the different configurations of bipolar transistors and MOSFET transistors or single transistor amplifiers. Now we will start building complex circuits where we have 2 or more transistors, and we will use all the insights that we have learned so far while we are building these new building blocks.